Soils basically is where you take soil, where you take a mother rock, parent material, and you actually will break it down. Okay, it's made up of inorganic material, and that is actually the rock portion. The organic matter, anything living, such as worms and bugs and critters like that, and the pore space in between where the particles are, and the most important is where water can infiltrate into the soil. This shows you our soil structure. If I were to go down, take a cross section down, you have the O, which is the horizon, which is up here where the grass is located. You have the A, which is up here. It's your topsoil, or called the horizon. It's rich in organic material. You have the B, horizon, which right here is zone of accumulation. C is your weathered soil, and R is your unweathered parent material. Or if I look at this one, it goes more in depth. In between A and B is the E, horizon, alluviation layer, and that is where you're going to find a little bit lighter in coloration from the topsoil, but you will find particles and bits from where the parent material is located. Oops. Okay. Our next one, we're going to look at different soil properties with each of these, and we're going to start first of all with infiltration. Infiltration is where water will penetrate and actually pass through different kinds of soils. Depending on the makeup of the soil will depend on how fast the water can actually penetrate it through it. If it has a high permeability, that means that there's high pore space in between there, and the water can actually pass through, where low permeability will have less pore space in between, and water will be caught or trapped in that particular area. Leaching just means the materials that are pulled out of the soil. The porosity or permeability is, again, that ability for water to pass through. The texture is the size of it, the structure, how it's shaped, and the pH. Let's take a look first of all at bulk density. This is another one. Bulk density just tells us how tightly packed the soil is. Usually you will take soil, you will dry it out, and you will determine the particle size and shape after it's been completely dried up. You can see right here we have one that has a higher bulk density to a less bulk density, and work our way down. Another characteristic is color. Some of our colors right here determine is by when you take soil, you have to wet it, cannot be dry, and you base it almost like a color scheme that we have paint chips. You have to compare it where the sun is shining from behind you, down on you. You can't be facing the sun. You turn your back to the sun, hold up the color chips, and then you see what it looks like color-wise. Some of our colors are used by the Munsell notation. You have your hue, your value, and your chroma. The hue is where it is on the color wheel. Your value is how light, faint to dark it is. And then chroma is the brightness of it. Soils that can vary greatly in color also determine what kind of mineral composition it contains. Here we have two different soils. When you see the real black colored soils right here, they tend to be rich in organic material. Here, these red soils tend to be high in iron, so it has high oxidation levels. Our soil structure is the next one. We have granular, columnar, prismatic, blocky, and platy. We have the first one right here where it's granulated. It'll fall through your fingertips really quick. Prismatic is where it is broken into layers that are in the vertical direction. Columnar as well. Blocky, just bigger chunks. And platy, again, instead of going vertical, it's going horizontal, broken plate boundaries. And here you can see again, soil also consistency can be broken up by loose, where it will fall through your fingers, friable, which means you can take it, it breaks apart in your hand, firm, it will not break apart, and extremely firm, you're going to have to take a hammer and beat it. Permeability is how fast water can actually move through soils. It is determined by the distance versus time, and also it determines also how much runoff will occur if a rain storm comes up. And here you can see a comparison down here. Here you have 1 meter down, simulating the different type of soils. Gravel, if water were to pass through gravel, it would take about 2 minutes. Sand, 2 hours. Silt, 200 days. Or clay, 200 years. The texture, again, is determined by the size of the particles. We have sand, silt, clay. And there is a fourth one called loam, and that is a mixture. Here is just showing a representation of sand to silt to clay. Sand, the best way is by a field test. Sand is very gritty, rough to the touch. Silt is floury, feels like almost baking soda or flour. And clay is very sticky. This is called the soil triangle, and we will try to practice this one in class, but it just shows the orientation where you will determine the type of soil. Clays, if you look over here on this one, are upright, so if I have 50, it will go across. Silt, you'll see that the numbers are angled. You go in the direction at which the numbers are. And then sand down here at the bottom are going up also at a slight left orientation coming upward. We also have soil quality. This is just showing you various soil components. First of all, clay has a very good nutrient capacity. It has a poor infiltration ability because there's very little pore space in between the particle to particle. Has a very good water holding capacity. The aeration's pretty good, and tilth is poor. Silt has a medium nutrient, medium infiltration, medium capacity, water holding capacity, and medium aeration. Sand has a poor nutrient value, has a good infiltration, has a lot of space in between pores so water can infiltrate it. It is a poor water holding capacity because water passes through very quickly, and very good aeration because of the pore space again, and good tilth. Loam has medium nutrient capacity, medium infiltration all the way through going across on this one. Our soil moisture is how much water content is found in the water, or actually in your soil, and it's based on the following factors: how much organic materials located in your soil, the pore spaces, the porosity, and also the capillary, its ability to allow water penetrate and pass through, and actually can pass upward in the soil. Soils also can have charges. Soils basically are negatively charged, and they typically will repel like charges, or opposite charges they're going to tend to attract.
Honey, I'm home.
Cations can be expressed within the soil, or can be exchanged within the soils. Okay, and this is also important with this cation exchange with the positive and negative charges of soils, essential for plant growth. Okay. pH is also the acidity, how acid or basic the soil is, and it determines the how much growth can be determined within the soil itself. For instance, plants. Hydrangea is a great example. If you have a hydrangea, which are like I call grandmother plants, if it is acidic, the plant color will be blue, but if it is basic, the color will actually turn to pink blooms. We know that if you dip it into pH paper, typically red is a acid color, blue is a base color, but in hydrangea it's actually the opposite. Also, acidic soils are usually associated with kind of different kinds of trees. Pine trees typically leave soils with the lower pH, very acidic soils. Fertility is also needed for nitrogen, phosphorus, for plant growth to grow. It is essential. A lot of times fertilizers are implemented or added back into soils. And also for our soil formation, soils develop in response to these things called CLORP, which is your climate, how much living materials are found there, your parent material, topography, and how much time it takes. So climate, again, is the important factor. So if we look back to our biome project, climate is how much temperature and precipitation is affected in an area. So that will determine it. Your living organisms are the ribosomes, your nematodes, any other kind of worms and things like that actually can help break down, decompose within there. Your parent material is your parent rock, the actual material before it's broken down, whether it's a sedimentary, igneous, metamorphic rock. And topography is just your landscape of it, its ability to drain. And time, the longer it takes, the more soil can actually form on there. We also have weathering processes that break it down. Your physical properties are temperature, where you can have frost wedging, you can have different kinds of properties to actually break it down physically. But chemically is where your acid rain and things like that will break it down. Examples are located here. Mass wasting is just another term for mass movement, and that's where gravity affects materials to actually break down through the process of wind, water, and in causing it to slip and dislocate from its original orientation. Erosion is a part of that process, and you can have sheet erosion where water is just falling down. You can have stream erosions, and also the neat one is with caves, where you can have your karst topography, where water is dripping down into your groundwater. It's withdrawn, and actually it will cause your limestones to form, and it creates sinkholes. We have different kinds of soil conservations, and I'll do that in a little bit later at a different time. Okay?